Okay, let's talk a little bit more about viscosity. And we'll start by talking about the units. So remember that the shear stress in a couette flow is the viscosity times the velocity of the top plate divided by the spacing L between the two plates. So let's rearrange this. To solve for the viscosity would be the shear stress times the length divided by the velocity. So then if we think about the units of viscosity, that would be the units of the shear stress, which is newtons per meter squared, times the length divided by the velocity, meters per second. So we can cancel one factor of meters here, and we get Newton per meter squared times a second, which you could also write as a Pascal times a second. So that's the official SI unit of viscosity, a Pascal second, but often you will instead see the unit of centipoise, where it's abbreviated CP, 1 centipoise is equal to 10 to the minus 3 Pascal seconds. And the reason that this is common is because the viscosity of water at room temperature is about 1 centipoise. So for H2O, let's make a little table here where we'll make a table of temperature in degrees Celsius versus viscosity in centipoises. And so I'm going to start with the middle entry of this table, which is 20 degrees Celsius, so that's room temperature. The viscosity of water is 1.005 centipoise. If you cool it down to just above freezing, so 0 degrees, the viscosity goes up quite a bit. It becomes 1.79 centipoises. If you heat it up, so it's just at the boiling point, 100 degrees, the viscosity goes down quite a bit to 0.28 centipoises. So you can see that the viscosity of water, and in fact of virtually all fluids, depends fairly strongly on temperature. Let's talk about an important practical application of that, which would be for motor oil. So when you have a car engine and you're trying to start it up, there are kind of two conflicting requirements for your motor oil. So when it's cold, that's going to mean that its viscosity is high, so high viscosity, because the viscosity gets bigger as the temperature goes down. And that, you can see, creates, if the viscosity is high, that creates a higher shear stress, meaning that your engine has to work harder to move the engine parts relative to one another. For example, to move the pistons relative to the cylinders. So this makes it hard to start your engine. Hard to start. On the other hand, when the motor oil gets too hot, then the viscosity is going to go down, and low viscosity fluids sort of run off of surfaces very quickly, and so it's going to give you poor coverage of those surfaces, and you want to keep all your surfaces covered with oil to prevent the metal from wearing down. So most of the time when you purchase oil, so oil viscosity rating for motor engines at least, it usually says something like 10W40. And the 10 is a measure of the viscosity. I'm not sure exactly what units that is. Maybe that's in centipoises. It sounds about right. But the W stands for in winter. So let's say we assume that this is in centipoises. It would be during the winter, meaning when you're starting your engine when it's cold in the winter, the oil behaves like a fluid with a viscosity of 10 centipoises. The other number is for the summer. And in other words, this is when it's hot out. The oil will behave like something that has a higher viscosity. So they've treated it with some chemical that kind of reverses the usual temperature dependence, at least when the engine is just being started. So when you're starting it in the summer, it will behave like something that has a relatively high viscosity, so that will counteract this poor coverage and allow the oil to coat things better. On the other hand, in the winter, when things are really cold, it will behave like something that has a lower viscosity. And so it partly cancels out the usual temperature dependence. And so that's why most of the time you want to buy this, it's called multi-grade motor oil. Okay, so next let's talk about the most important number when it comes to fluids, which is the Reynolds number. So let me ask the following kind of conceptual question. I don't really expect you to be able to answer it, but this is the question that we're going to try to answer over the next 10 minutes or so. If we imagine we have a glass of water, so here's a glass of water and a glass of air. So same kind of glass, but it's just filled with air. And we're going to stir them up. So we stir the water and we stir the air in the same way. And we ask which one comes to rest first. Comes to rest first after we stop stirring. Does the water come to rest first, or does the air come to rest first? So a couple of things to bear in mind, that the viscosity of water at room temperature is about 1 centipoise. The viscosity of air, let me ask you a concept test. Before I tell you, think about this on your own. At room temperature, do you think the viscosity of air is higher or lower than the viscosity of water? And let's look back at this equation, which is the one that basically is defining our viscosity. And remember that tau is the force per unit area. If I'm trying to move one surface relative to another surface that's a distance L away. So think about that on your own briefly. Does the viscosity of air, is that higher or lower than that of water at room temperature? So hopefully you've realized that it's a lot easier to move one surface past another if they're in air than in water, so it's lower. In fact, at room temperature, the viscosity of air is about 0.02 centipoises. So there are two kind of conflicting things that you got to think about in this conundrum of whether the water or the air will come to rest first after we stop stirring. The water has the higher viscosity, so that would argue that the viscosity tends to sort of slow things down, so you'd think because of that it's going to come to rest first. On the other hand, the water also has higher density and therefore higher momentum, and so that would tend to make it continue to circulate longer. So to think about this, we're going to define the Reynolds number. And the Reynolds number is something that is used to treat things kind of semi-quantitatively and to decide what regime of flow are you in. And so to define the Reynolds number, we consider a cube of fluid which is part of a flow in a pipe. And we're going to, so here's our cube. And let's say that the cube has edge length L. And we want viscosity to bring it to a stop in a distance L. That's the way we're defining the Reynolds number. And so let me define, I'm going to say F needed is the viscous force. So this is part of a flow, right? So it's moving with some velocity v like this. F needed is the viscous force needed to stop the cube as it moves through a distance equal to that edge length, through a distance L. And we're going to make, so first let's think about the force that's required to do that stopping. Force required would be the mass times the acceleration over that period. And so that's equal to the mass, which is rho L cubed, right? L cubed is the volume of the cube, times the acceleration. The average acceleration would be v over whatever time period it takes to come to rest. We're going to say that that time period is about the distance that it travels, L, divided by v. And so if I plug that in here, the force required is about rho times this factor of L here is in the denominator, so that's going to cancel one of these factors here. So that's going to be L squared, and then this V is going to cancel with that V. So it's just, oh, I'm sorry, this V doesn't cancel because it's in the denominator. The denominator comes up, so it's going to be rho L squared V squared. And now let's think about the viscous force that's available. The available force we can get that from the shear stress that's associated with the viscous force. So the shear stress is force over area, which of course that would be force over L squared, because we're talking about a cube here. And that's eta, the viscosity, times V over L from our equation that basically defines eta. And so I could rearrange this equation to solve for F. F is equal to eta V L. And so now the Reynolds number is the ratio of the F needed divided by the F available. So if we plug these in, I guess I should have said F required to keep with the same terminology that I used before. F required over F available, so that'd be rho L squared V squared. That's the F required to stop the cube in a distance L, roughly at least, divided by eta VL. And do a little canceling, like so. So it's rho L over eta. And that is the definition of the Reynolds number, which we abbreviate RE. This is not R sub E, it's capital R little e. So it's unusual, maybe the first time you've encountered a symbol that uses two letters for it. So this is the definition of the Reynolds number. And I would say that that's a 2-star box. It's really, as I say, the most important number when it comes to thinking about fluids. Another way to think about it is that Reynolds number, RE, is basically a measure of your momentum, because that's related to the force that's required. So force is having to do with momentum, or the momentum of the block, I should say, divided by the viscosity. So a high Reynolds number means you have a lot of momentum relative to your viscosity. Okay, so now let me ask what might be a fairly challenging concept test. If the Reynolds number is large, is turbulent or laminar flow more likely? So I'd like you to pause the video now and think about this on your own, and only come back when you have a tentative answer, or you've just decided that you're not going to be able to get an answer thinking only on your own. Okay, so let's talk about this together. Let's imagine we have a flow pattern where we've got water that's kind of going around a curve, because maybe the pipe that it's in is curved, but what I mean to be indicating is these are kind of streamlines like this. And let's think about a little piece of the water here, and what's going to happen to it if it has a large momentum. So large momentum means that it tends to continue flowing moving in a straight line rather than curving, and so it's going to, in a sense, collide with these other volumes of water, and that collision is going to tend to cause turbulence. So large Reynolds numbers are associated with turbulence. And experimentally, we find that most of the time, if the Reynolds number is greater than about 10,000, then you get turbulence. And if it's less than 100, you get laminar flow. And so there's a big region in between there where, depending on the exact circumstance, the behavior might be turbulent or laminar, or some kind of behavior that's not clearly either one. Now, when you're calculating the Reynolds number, there are two parts of it that are pretty obvious what you plug in: the density and the viscosity. Those are things that you just look up, being aware that density depends very slightly on temperature, viscosity depends pretty strongly on temperature. But then you also have to pick what to plug in for the length. And that's sometimes a little bit tricky, but good rule of thumb that length is the diameter of a pipe, if you're talking about flow through a pipe, or the diameter of, let's just call it a rock, if you're talking about water flowing around a rock, like in a river. Okay, I think that's a good place to pause this recording.